March 1945. A proving ground outside Berlin. 3 veteran German tank commanders stood in a semicircle around an American Sherman tank, their arms crossed, expressions somewhere between contempt and curiosity. They had been summoned from the collapsing Eastern and Western fronts for a special assignment: evaluate a captured enemy tank. But this wasn't just any Sherman. This was the M4A3E8, what American tankers called the EZ-8. The latest evolution of a tank the Germans had learned to fear far more than they publicly admitted. Hauptmann Klaus Becker, a Panther commander with 2 years of combat experience, walked slowly around the Sherman. He had destroyed 4 Shermans in combat. He knew their weaknesses intimately. Or thought he did. "It looks the same as the others," Becker said to his companions. "Same basic hull. Same turret shape. The Americans just keep building the same tank over and over." Oberleutnant Werner Schmidt, who had fought Shermans in Normandy, pointed at the suspension. "Wait. Look at the tracks and road wheels. That's different. Wider tracks. Different suspension arrangement." The third officer, Lieutenant Friedrich Vogel, examined the gun. "And that's a 76mm gun. Not the short 75. We've faced these before. More dangerous, but still a Sherman." A civilian engineer from the Waffenamt, Germany's weapons testing agency, approached with a clipboard. His name was Heinrich Müller, and he had evaluated dozens of captured Allied vehicles during the war. "Gentlemen," Müller began, "this specific variant has only recently appeared in significant numbers. Intelligence reports suggest the Americans are replacing their older Shermans with this model as quickly as possible. High Command wants to know why. What makes this one special?" Becker laughed, but it was a bitter sound. "What makes it special is that there are thousands of them and we have barely enough fuel to drive our Panthers to the front. That's what makes it special." Müller didn't smile. "You'll have fuel for this evaluation. 3 days of intensive testing. I want this tank driven, fired, maintained, and compared directly to a Panther. By the end, I want to know definitively whether our propaganda about Sherman inferiority is accurate or merely wishful thinking." The 3 tank commanders exchanged glances. The question was dangerous because the answer might be uncomfortable. Germany had spent years telling its soldiers that German tanks were superior. That Allied tanks were quantity over quality. That German engineering excellence would triumph over American mass production. But it was March 1945. Germany was losing. Badly. And perhaps it was time to understand why. Over the next 72 hours, these German tankers would drive the EZ-8 through every test they could devise. They would push it to its limits and beyond. They would tear it apart and examine every component. They would compare it directly to their vaunted Panther tank. And what they discovered would shatter their assumptions about German technical superiority. This is not a story about raw statistics or armor thickness. This is a story about the moment when experienced German tank commanders confronted a truth they had been avoiding: that the Americans had built a tank that was, in many ways that mattered in actual combat, better than Germany's best. The EZ-8 wasn't the most heavily armored tank. It wasn't the most powerful. It didn't have the thickest gun. On paper, the German Panther was superior in almost every measurable category. But war isn't fought on paper. War is fought in mud and snow, across broken bridges and bombed-out roads, by exhausted crews who need their equipment to work when it matters most. And in those conditions, the EZ-8 Sherman revealed a philosophy of tank design that the Germans had never fully embraced: that reliability, maintainability, and crew effectiveness mattered more than maximum performance specifications. The Sherman M4A3E8 represented the culmination of American tank development during World War II. It incorporated every lesson learned from years of combat. The HVSS suspension system that gave it its EZ-8 nickname. The high-velocity 76mm gun. The wet ammunition storage that finally solved the Sherman's tendency to catch fire. The improvements in armor layout and crew protection. But more than specific features, the EZ-8 embodied a design philosophy. build a good tank that crews can rely on, maintain in the field, and fight effectively day after day. Don't pursue theoretical perfection. Pursue practical excellence. The German Panther, by contrast, was a magnificent engineering achievement that was also a maintenance nightmare, a fuel hog, and increasingly unreliable as Germany's manufacturing quality collapsed under Allied bombing and resource shortages. On paper, the Panther should win every engagement. In reality, Shermans were destroying Panthers with increasing regularity by 1945, and German tank commanders were beginning to understand why. Becker climbed into the EZ-8's driver position, adjusted the seat, and started the engine. The Ford GAA V8 roared to life with a sound distinctly different from German engines. Smoother. More refined. Almost like a truck engine rather than a tank engine. He engaged the transmission and pressed the accelerator. The Sherman lurched forward, then accelerated smoothly across the test ground. And in that first 30 seconds of driving, Klaus Becker felt something he hadn't expected. The EZ-8 handled better than his Panther. Over the next 3 days, that initial impression would be confirmed again and again. The EZ-8 wasn't just a good tank. In the conditions of 1945, fighting in the ruins of Germany with limited fuel, spare parts, and maintenance capacity, it was arguably the better tank. This is the story of how German tankers learned that lesson. How they tested, analyzed, and ultimately had to admit what their propaganda had denied. The Americans had built a tank that worked. And in total war, a tank that works beats a tank that's theoretically superior but constantly breaks down. The EZ-8 was about to reveal all its secrets. And those secrets would be painful for German engineers and tankers to accept. The story of how Germany obtained an intact M4A3E8 Sherman begins in the chaos of the Battle of the Bulge's aftermath, in late January 1945. The German offensive through the Ardennes had failed. What began as Hitler's desperate gamble to split Allied forces and capture Antwerp had collapsed into a fighting retreat. American forces were pushing back, reclaiming ground, and advancing toward the Rhine. Near the town of Houffalize in Belgium, elements of the U.S. 2nd Armored Division were conducting pursuit operations against withdrawing German forces. Among their tanks was an EZ-8 Sherman from Charlie Company, 66th Armored Regiment, commanded by Sergeant Thomas Mitchell. On January 28, Mitchell's tank hit a concealed German Teller mine while navigating a narrow forest road. The explosion destroyed the right track and damaged the final drive. The tank slewed sideways and came to rest half in a ditch, immobilized but otherwise intact. Under fire from German positions in the tree line, Mitchell's crew had to make a quick decision. They grabbed their personal weapons, destroyed the radio with thermite grenades, and evacuated the tank. Standard procedure was to disable the gun and destroy the engine, but German machine gun fire was raking their position. They ran. Mitchell assumed recovery vehicles would retrieve the tank within hours, or that if the position became untenable, engineers would destroy it. What he didn't know was that a German counterattack that evening would temporarily retake that section of road. A Kampfgruppe from the 2nd SS Panzer Division found the abandoned Sherman at dawn. The company commander, Hauptsturmführer Joseph Dietrich, immediately recognized its value. This wasn't an early model Sherman. The suspension was different. The tracks were wider. The gun was the long 76 mm. Dietrich called for recovery equipment. Under cover of morning fog, German crews attached cables and towed the damaged Sherman behind their lines. Within 6 hours, it was loaded onto a heavy transport and moving east, away from the front. The tank's journey took it first to a Wehrmacht maintenance depot near Koblenz, where mechanics made temporary repairs to assess its condition. The mine damage was significant but localized. The track could be replaced. The final drive needed repair. But the engine, transmission, turret, and all major systems were undamaged. More importantly, this was clearly a very recent production model. The paint was fresh. The equipment was new. The odometer showed less than 300 kilometers of operation. This was a frontline tank straight from American production, incorporating the latest modifications. A report went up the chain to the Waffenamt in Berlin. The response was immediate. Send the tank to Kummersdorf Proving Grounds for full evaluation. Priority orders. Every other test was to be delayed. By mid-February, the EZ-8 arrived at Kummersdorf, one of Germany's primary vehicle testing facilities located about 30 kilometers south of Berlin. The facility was still partially operational despite Allied bombing, protected by extensive camouflage and air defenses. Heinrich Müller, the senior engineer assigned to evaluate captured Allied equipment, received the tank with considerable interest. He had examined dozens of Shermans during the war, but most were early variants or heavily damaged. Getting a nearly new EZ-8 intact was extraordinarily rare. Müller assembled a team, 3 combat-experienced tank commanders, 2 automotive engineers, a weapons specialist, and several mechanics. They would have 3 days for intensive evaluation before the tank would be moved to a more secure location away from Allied bombing range. The 3 tank commanders selected were not chosen randomly. Hauptmann Klaus Becker had commanded Panthers on the Eastern Front and had personally knocked out 4 Shermans. Oberleutnant Werner Schmidt had fought in Normandy and the retreat across France, encountering hundreds of Allied tanks. Lieutenant Friedrich Vogel was a gunnery instructor who had trained panzer crews for 2 years. All 3 men were experienced professionals who understood tanks intimately. Their opinions would carry weight. The Kummersdorf facility also provided something crucial for comparison: a Panther OSF-G tank, a late production model similar to those currently fighting on both fronts. The plan was to test the Sherman and Panther side by side under identical conditions. On March 10, 1945, the evaluation began formally. Both tanks were fueled, armed, and made ready for testing. The EZ-8 had been repaired by German mechanics using a replacement track and final drive components cannibalized from another captured Sherman. It ran smoothly, showing no signs of the mine damage that had disabled it weeks earlier. Müller gathered his team around both tanks for initial briefing. "Gentlemen, this is not propaganda work. I don't want to hear what you think High Command wants to hear. I want the truth. If this Sherman is inferior, document why. If it's superior in any way, document that too. We need accurate information, not comforting lies." It was a remarkably frank statement for March 1945, when questioning German superiority in anything could be dangerous. But Müller was a scientist, not a soldier, and he understood that self-deception was a luxury Germany could no longer afford. Becker walked around both tanks, comparing them visually. The Panther was larger, heavier, more imposing. Its sloped armor and long 75mm gun looked formidable. The Sherman seemed smaller, less aggressive, almost utilitarian by comparison. But Becker had learned not to trust appearances. He had seen too many inferior Allied tanks destroy German panzers through weight of numbers, air support, and competent tactics. "Let's begin with basic mobility," Müller announced. "Hauptmann Becker, you'll drive the Sherman first. Schmidt, you take the Panther. I want both of you to run the obstacle course, then we'll switch and you'll run it again in the opposite tank. I want comparative impressions from the same drivers." Becker climbed into the Sherman's driver position. The interior was cramped but well organized. The controls were logically arranged. The seat adjusted easily. He started the Ford GAA engine and felt it settle into a smooth, powerful idle. He had driven captured Shermans before, but those had been earlier models. This felt different somehow. More refined. More confident in its power delivery. Müller's voice came over the radio. "Whenever you're ready, Hauptmann. Take it through the course at combat speed." Becker engaged the transmission, released the brake, and pressed the accelerator. What happened next would begin to change his understanding of American tank design. Before the actual testing began, Müller wanted to document what his evaluation team expected to find. He gathered the 3 tank commanders and asked them to describe their preconceptions about the Sherman based on their combat experience and German intelligence assessments. Hauptmann Becker spoke first. "The Sherman is a mass-produced tank designed for quantity over quality. It's fast on roads but less capable cross-country than our panzers. The armor is adequate against smaller caliber weapons but vulnerable to our long 75s and 88s. Early models had a dangerous tendency to catch fire when penetrated, earning the nickname Tommy Cooker, among our troops. He paused, then added honestly, but I've also seen Shermans absorb incredible punishment and keep fighting. And they're always accompanied by air support, artillery, and infantry in numbers we can't match. So the tank itself is only part of why they're effective. Oberleutnant Schmidt nodded. In Normandy, we destroyed many Shermans. Sometimes 5 or 6 for every Panther we lost. But there were always more Shermans. They kept coming. And by the end of a battle, even if we won tactically, we had lost Panthers we couldn't replace while the Americans just brought up more Shermans. Lieutenant Vogel added the gunnery perspective. The Sherman's gun has evolved. Early models with the short 75mm were no threat to Panthers frontally. But this 76mm with the newer ammunition can penetrate our frontal armor at certain angles and ranges. It's become dangerous. Muller documented these observations, then asked about specific technical expectations. The Sherman uses a radial aircraft engine in most versions, correct? He asked. The earlier ones, yes, Becker confirmed. The right radial. Very tall, which makes the tank's profile high. But this variant has a different engine. Intelligence briefs mentioned a V8 gasoline engine. Lower profile. What about the suspension? Muller pointed to the Easy 8's running gear. This doesn't look like the vertical volute spring suspension on earlier Shermans. Schmidt examined it closely. No, this is new. Horizontal volute springs, I think. And the tracks are much wider. Perhaps 23 or 24 inches instead of the standard 16. This suggests they're trying to improve cross-country performance and reduce ground pressure. The engineer made notes. So your expectation is that this variant will have better mobility than earlier Shermans? Possibly, Schmidt said. But still inferior to the Panther's torsion bar suspension. Our system is more sophisticated. Muller then directed their attention to the Panther sitting nearby. And what are your expectations for how the Panther will perform in comparison? This question produced immediate confidence from all 3 officers. The Panther is superior in armor protection, Becker stated firmly. 80mm of sloped frontal armor versus the Shermans. What, 64mm? And our armor is better sloped. The Panther's gun is superior, Vogel added. Our 75mm KWK-42 has higher velocity and better penetration than the American 76mm. At normal combat ranges, we can destroy Shermans frontally while they need side or rear shots on us. The Panther is faster, Schmidt said. Top speed of 55 km/h versus the Sherman's 48. More powerful engine. Better power-to-weight ratio. Muller listened to this recitation of German advantages, then asked a more pointed question. If the Panther is superior in all these ways, why are we losing tank battles in the West? Silence fell over the group. It was a question that had obvious answers, but saying them aloud was uncomfortable. Finally, Becker spoke carefully. Numbers. Air superiority. Fuel shortages. Mechanical reliability issues with late production Panthers. Crew training quality declining as experienced tankers are lost. Many factors beyond the tanks themselves. Mechanical reliability issues, Muller repeated, writing it down. Elaborate on that, please. Becker chose his words carefully. Early Panthers were excellent machines. But current production Panthers have quality control problems. Transmissions fail. Final drives break. Engine cooling systems leak. Some Panthers don't make it to the front under their own power. Schmidt added, in Normandy, we lost as many Panthers to mechanical failure as to enemy action. Perhaps more. The Americans target Panthers specifically because they know we can't replace them. Every Panther destroyed or broken down is a permanent loss. This was closer to heresy than analysis, admitting that German technical superiority might be more propaganda than reality. But Muller had created an environment where honesty was acceptable. So one thing we'll be evaluating, Muller said, is whether American design philosophy prioritizing reliability over maximum performance produces better combat results than our approach of pursuing theoretical excellence. He gestured to both tanks. The Panther on paper is the better tank. More armor, better gun, faster. But if it breaks down or requires constant maintenance, does that matter? If the Sherman is good enough and never breaks, which is truly superior? It was the fundamental question that would guide the entire evaluation. The team spent the rest of the morning conducting visual inspections of both tanks, documenting every observable difference. The contrast in design philosophy was immediately apparent. The Panther was a work of engineering ambition. Complex interleaved road wheels. Sophisticated torsion bar suspension. Carefully shaped armor plates. Precision-manufactured components throughout. It was a tank designed by engineers pursuing optimal performance. The EZ-8 Sherman was simpler in almost every way. The suspension used large, obvious coil springs. The armor was thick flat plates welded together at angles. The tracks were wide rubber and steel affairs that looked almost agricultural. It was a tank designed by engineers who understood factories and maintenance depots as well as battlefields. The Sherman looks like it was designed to be repaired by mechanics with basic tools, one of the German engineers observed. Everything is accessible. Components are modular. I could probably replace the engine in a few hours. Try that with a Panther, Becker muttered. Removing a Panther engine is a 2-day job requiring specialized equipment. As the morning progressed, the German evaluation team's initial contempt for the Sherman began to erode slightly. The tank was clearly well made. The welds were solid. The components fit together properly. Nothing looked crude or hastily assembled despite being mass-produced. Muller made a note. First impression, the Sherman M4A3E8 appears to be a mature design incorporating years of combat feedback. Not cutting-edge technology, but refined, practical engineering. The question is whether practical engineering defeats theoretical excellence in actual combat conditions. By noon, the team was ready to begin active testing. Becker climbed into the Sherman's driver's seat one more time, while Schmidt took the Panther. They would start with the most basic test, driving both tanks through the obstacle course to compare mobility and handling. What they were about to discover would surprise all of them. The Kummersdorf test course was brutal. Deep ruts, steep inclines, log obstacles, ditches, and a section of broken concrete meant to simulate bombed roads. It had been designed to push tanks to their limits. Hauptmann Becker sat in the EZ-8's driver position, hands on the controls, engine idling. Through his periscope, he could see the obstacle course ahead and, to his right, Oberleutnant Schmidt in the Panther waiting for the start signal. Muller's voice crackled over the radio. On my mark, both tanks proceed through the course at maximum practical speed. Ready, mark. Becker hit the accelerator. The Ford GAA engine responded immediately, and the EZ-8 surged forward. The acceleration was smooth, linear, no hesitation. He shifted through the gears quickly, and the Sherman built speed across the flat starting section. The Panther alongside him accelerated faster initially. It had more power, and Becker could see it pulling slightly ahead. But then they hit the first obstacle section, a series of deep ruts cut diagonally across the course. Becker braced himself for the jarring impact he remembered from earlier Shermans. The vertical volute spring suspension on older models gave a harsh, choppy ride over rough terrain. But the EZ-8's HVSS suspension absorbed the ruts with remarkable smoothness. The tank pitched and rolled, but the motion was controlled, damped. Becker could maintain his speed through the section without being thrown around the compartment. He glanced right and saw the Panther bouncing violently through the same ruts. Schmidt was clearly being hammered by the impacts despite the Panther's sophisticated torsion bar suspension. Interesting, Becker muttered to himself, pushing the Sherman harder. The next obstacle was a steep incline, perhaps 30 degrees, with loose soil at the crest. Becker kept his momentum up, and the EZ-8 charged up the slope. The wide tracks bit into the soil, and the tank crested the hill without slipping or losing traction. The Panther made it up as well, but Becker noticed it had to work harder, the tracks churning more aggressively to maintain grip. Then came the log obstacles, heavy timber laid perpendicular to the direction of travel, simulating fallen trees or battlefield debris. Becker hit the first log at speed. The Easy 8's nose lifted, the suspension compressed, then the tank rolled over the obstacle smoothly and continued without hesitation. Behind him, through the dust, he could see the Panther navigating the same logs more carefully, taking them at reduced speed. The broken concrete section was next. Chunks of pavement and rubble simulating a destroyed road. This was where Becker expected the Sherman to struggle. The Panther's longer wheelbase and sophisticated suspension should give it an advantage here. But as Becker drove through the section, he realized the Easy 8 was handling it beautifully. The HVSS suspension kept the tracks in contact with the ground even over the most broken terrain. The ride was rough but controllable. He could maintain 15 kilometers per hour through conditions where earlier Shermans would have been limited to half that. The final obstacle was a ditch crossing, a trench 2 meters wide that had to be crossed at an angle. Becker approached it with confidence, angled the Sherman properly, and drove across. The tank dipped into the ditch, the suspension compressed fully, then extended as the tracks climbed out the far side. Smooth. Controlled. No drama. Both tanks completed the course and pulled up at the finish point. Muller and his team were waiting with stopwatches and clipboards. Sherman, 4 minutes, 38 seconds, Muller announced. Panther, 4 minutes, 52 seconds. Becker climbed out of the Sherman, surprised. The Sherman was faster? By 14 seconds over the course, Muller confirmed. Now switch tanks and run it again. 30 minutes later, after both commanders had driven both tanks through the course, the results were even more striking. Both drivers reported that the Sherman felt faster and more controllable over rough terrain despite the Panther having more power. The suspension is remarkable, Becker admitted to the group. The HVSS system absorbs impacts that would slow the Panther down. Over rough ground, the Sherman maintains speed better because the crew isn't being thrown around and the tracks stay in better contact with the surface. Schmidt agreed. In the Panther, I had to slow down for obstacles. In the Sherman, I could maintain speed. The wider tracks also help. Lower ground pressure means less sinking in soft ground. Muller ordered his engineers to examine the HVSS suspension system in detail. What they found impressed them significantly. The horizontal volute spring suspension used large horizontal coil springs mounted to trailing arms. Each road wheel had independent suspension travel. The system was simple mechanically but sophisticated in its execution. The springs were protected inside armored housings, unlike the Panther's torsion bars that ran across the hull floor. This suspension has several advantages, one engineer reported. First, it's simple to maintain. If a spring or trailing arm is damaged, you can replace just that component without affecting the rest of the suspension. Second, the springs are outside the hull, so they don't take up interior space. Third, the independent suspension allows excellent ground contact over rough terrain. He pointed to the Panther's suspension. Our interleaved road wheels and torsion bars are more complex. If one torsion bar fails, repair is difficult because they overlap inside the hull. And in mud or snow, debris packs between the interleaved wheels and can freeze solid overnight, immobilizing the tank. Becker remembered this problem from the Eastern Front. Panther crews regularly had to build fires under their tanks in winter to thaw frozen suspension systems before they could move in the morning. The Sherman's wheels are widely spaced, the engineer continued. Mud and debris fall through naturally. Even in winter conditions, ice doesn't pack in the same way. They conducted specific tests to measure suspension performance. Maximum vertical wheel travel. The Easy 8 suspension could compress and extend over 20 centimeters. The Panther's torsion bars allowed similar travel but less damping of the motion. Cross-country speed tests over measured courses showed the Easy 8 consistently matching or exceeding the Panther's speed despite having 120 less horsepower. The suspension and wider tracks were force multipliers for the available power. Maintenance access was another revelation. The HVSS suspension components were mounted externally. A two-man crew could replace a damaged trailing arm and road wheel in under an hour with basic tools. On the Panther, if you damage a torsion bar, you need to remove interior components, possibly remove other torsion bars, and the repair takes most of a day with proper tools and a maintenance facility, Muller noted. The Sherman can be repaired in the field. The German team conducted final tests pushing both tanks to their limits. They drove them through deep mud, up extreme slopes, across tank ditches. The EZ-8 matched or exceeded the Panther's performance in every test. Becker summarized it best: "The Panther has more power, but the Sherman uses its power more effectively. The suspension is the reason. American engineers didn't try to build the most sophisticated suspension. They built one that works reliably and gives the tank excellent mobility with simpler mechanics." Muller was already writing his preliminary report. Conclusion on mobility: the M4A3E8 Sherman demonstrates superior practical mobility compared to Panther OSF-G despite lower power output. Contributing factors: HVSS suspension system, wider tracks reducing ground pressure, simpler maintenance requirements, and better cross-country performance. The American approach of optimizing the complete system rather than maximizing individual specifications produces superior combat mobility. It was only day one of testing, and already the German evaluation team was confronting uncomfortable truths about their design philosophy. Day 2 of the evaluation focused on what German tankers considered the most critical aspect of any tank: its ability to kill enemy armor. The EZ-8 mounted the M1A2 76mm high-velocity gun, a significant upgrade from the short 75mm that had armed earlier Shermans. The question was, how did it compare to the Panther's fearsome 75mm KWK-42L/70? On paper, the German gun was superior. The KWK-42 fired a smaller diameter shell at much higher velocity, giving it better armor penetration at range. But Lieutenant Vogel, the gunnery specialist, wanted to test actual combat effectiveness, not just ballistic tables. The test range had been set up with captured T-34 hulls as targets at various ranges: 500 meters, 1,000 meters, and 1,500 meters. Both tanks would engage the same targets, and accuracy, penetration, and rate of fire would be measured. But first, Vogel wanted to examine the American gun closely. The M1A2 76mm was mounted in the Sherman's turret with a gyro stabilizer system. Vogel had heard of this feature but never seen it in action. German tanks had no equivalent technology. "Explain how this stabilizer works," Vogel asked the engineer examining the system. "It's a gyroscopic mechanism that keeps the gun relatively stable in the vertical plane even when the tank is moving," the engineer explained. "It doesn't lock the gun perfectly steady, but it reduces movement enough that a skilled gunner can fire accurately while the tank is in motion." Vogel was skeptical. "Firing on the move is rarely effective. We teach our gunners to halt, acquire the target, and fire. Why complicate the system with stabilization?" "Let's test it," Muller suggested. "We'll have both tanks engage targets while moving and while stationary. Then we'll see if the stabilizer provides any practical advantage." The stationary firing tests came first. The Panther's KWK-42 performed excellently, as expected. At 500 meters, Vogel placed 3 shots within a 1-meter circle on the target hull. At 1,000 meters, accuracy remained good. At 1,500 meters, the high-velocity gun still achieved consistent hits. The EZ-8's 76mm gun also performed well, though not quite matching the Panther's extreme range accuracy. At 500 meters, it was nearly equal. At 1,000 meters, slightly less precise. At 1,500 meters, noticeably less accurate. "The German gun has better long-range performance," Vogel concluded. "As expected." But then Muller changed the test parameters. "Now engage targets while moving at 15 kilometers per hour." This was where everything changed. Hauptmann Becker took the Sherman's gunner position. As the tank rolled across the range, he acquired a target through the gun sight. The gyro stabilizer kept the sight relatively steady despite the tank's movement. He made minor adjustments, waited for the optimal moment as the stabilizer damped the motion, and fired. Hit. Direct center mass on the target at 500 meters. He traversed to a second target. Fired again while moving. Another hit. Then Schmidt tried the same engagement from the Panther. Without stabilization, the sight bounced and swayed as the tank moved. He attempted to time his shot, but the shell went wide. He tried again. Closer, but still a miss. On the third attempt, he scored a hit, but it took 3 times as long as Becker's successful engagement. The stabilizer is a significant advantage in mobile warfare, Vogel admitted, making notes. It doesn't guarantee hits, but it dramatically improves the probability of hitting while moving. And it reduces the time needed to achieve a first-round hit. They tested fire control systems next. The EZ-8 had a sophisticated system by Sherman standards, a periscopic gun sight with range estimation, a gunner's quadrant for precise elevation, and most impressively, good crew coordination facilitated by an excellent intercom system. The Panther's fire control was theoretically superior, with precision optics and range-finding equipment. But in practice, the Sherman system was easier to use and faster to employ. The American system is designed for average gunners, Vogel observed. Everything is straightforward. Clear markings. Simple procedures. A crew with basic training can achieve acceptable accuracy quickly. He compared it to the Panther's system. Our system is more sophisticated but requires extensive training to use effectively. An expert German gunner with a Panther will outshoot an average American gunner with a Sherman. But we no longer have mostly expert gunners. We have inexperienced crews. The Sherman system works better with the crews we actually have, not the crews we wish we had. The ammunition was another critical factor. The EZ-8's 76mm gun could fire several types of ammunition, but the most significant was the HVAP round, high-velocity armor-piercing. The German team tested captured HVAP ammunition against armor plate. At 500 meters, it penetrated 130 millimeters of vertical armor. That was enough to penetrate the Panther's frontal armor at certain angles. "This is dangerous," Becker said quietly, examining the penetration test results. Earlier Shermans couldn't threaten Panthers frontally except at very close range. This gun with HVAP can penetrate our frontal armor at combat ranges if the angle is right. Vogel nodded. It changes the tactical equation. Panthers can no longer assume frontal immunity against Shermans. We have to respect this gun. The rate of fire comparison also favored the Sherman in practical terms. The Panther's gun could theoretically fire faster, but ammunition stowage and crew positions made sustained rapid fire difficult. The EZ-8's turret layout, with the loader positioned efficiently and ammunition readily accessible, allowed a good crew to maintain 8 to 10 aimed shots per minute. "Rapid fire matters," Schmidt observed. "In combat, the tank that shoots first and shoots accurately usually wins. If the Sherman can fire 3 times while we fire twice, that's a significant advantage." The gun mantlet design revealed another difference in philosophy. The Panther's mantlet was thick and well armored, but created a shot trap where incoming rounds could deflect downward into the thinner hull roof armor. The EZ-8's mantlet was simpler but didn't create the same shot trap geometry. It was adequate armor, without the vulnerability of the German design. After 2 days of gunnery testing, Vogel wrote his assessment. The Panther's KWK-42 is superior in penetration and extreme range accuracy. However, the Sherman's M1A2 76mm with gyrostabilization and HVAP ammunition is more effective in typical combat engagements under 1500 meters. The stabilizer allows accurate fire on the move, which is decisive in fluid combat. The simpler fire control system allows average crews to achieve combat effectiveness faster. Overall combat effectiveness slightly favors the Sherman despite the Panther's superior ballistic performance. It was a remarkable admission from a German gunnery expert that the theoretically inferior American gun was more dangerous in actual combat. On the third morning of evaluation, Heinrich Müller directed his team to focus on what he considered the most critical aspect of tank design: reliability. Gentlemen, Muller began, a tank that achieves maximum performance for 100 kilometers before breaking down is less valuable than a tank that achieves adequate performance for 1,000 kilometers without failure. Let's examine what makes these engines work, and more importantly, what makes them stop working. The team began by removing the engine covers from both tanks. The contrast was immediate and striking. The Easy 8's Ford WWII sat low in the engine compartment, accessible from above through large hatches. It was a massive aluminum block engine displacing 1,100 cubic inches and producing 500 horsepower. Despite its power, it looked almost simple. 8 cylinders in AV configuration, conventional overhead valves, straightforward cooling system. The Panther's Maybach HL230 was a very different machine. AV12 producing 700 horsepower from 1420 cubic inches, it was a sophisticated piece of engineering with complex timing systems, intricate cooling passages, and precision-manufactured components throughout. Let's start with a basic question, Muller said. How long does it take to remove and replace each engine? The mechanics went to work. For the Sherman, they disconnected fuel lines, electrical connections, cooling hoses, and exhaust pipes. They unbolted the engine mounts. Using a hoist, they lifted the entire Ford GAA engine out of the compartment in one piece. Total time, 2 hours and 15 minutes. The Panther engine removal was far more complex. The mechanics had to remove additional components just to access the engine mounts. The cooling system was integrated in ways that required careful disconnection. Multiple accessory drives had to be detached. When they finally lifted the Maybach out, they had spent 6 hours and 40 minutes. In combat conditions, a Sherman can receive a new engine and be back in action the same day, Becker observed. A Panther needs days in a maintenance facility. They examined both engines in detail on the workshop floor. The Ford GAA's construction impressed the German engineers immediately. This is an aluminum engine designed for mass production, one engineer noted. Look at the casting quality. Uniform thickness. Clean internal passages. The bearing surfaces are excellent. This engine was made to be manufactured by the thousands. The Maybach HL230, by contrast, showed signs of the declining quality control plaguing late-war German industry. The castings had inconsistencies. Some machine surfaces showed tool marks indicating rushed production. The tolerances varied between components. This particular Maybach is from late 1944 production, the engineer said, checking serial numbers. Quality has degraded significantly compared to earlier engines. We're no longer able to maintain pre-war manufacturing standards. They measured wear patterns on both engines. The Sherman's Ford GAA showed approximately 300 kilometers of operation based on its odometer reading. The wear on bearings, pistons, and cylinder walls was minimal and even. The Panther's Maybach showed approximately 800 kilometers of operation, but the wear patterns were concerning. Uneven bearing wear. Scoring on cylinder walls. The final drive showed signs of stress beyond normal operational use. The Maybach is operating near its limits constantly, a mechanic observed. The engine produces excellent power, but the drivetrain struggles to handle that power reliably. The final drives are the weak point. They fail regularly under combat conditions. Muller had obtained failure rate data from maintenance units. The statistics were sobering. Panther final drives averaged 150 kilometers before requiring overhaul or replacement. The Sherman's final drives averaged over 3,000 kilometers. Why such a dramatic difference? Muller asked. The engineering team analyzed both systems. The answer was partly design, partly manufacturing quality, and partly philosophy. The Panther's final drives were complex, precision-manufactured units designed to handle the tank's 45-ton weight and 700 horsepower. But they were also made from materials that Germany was increasingly unable to produce to proper specifications. Hardened steel gears required specific alloys and heat treatment. Late-war production couldn't maintain these standards. The Sherman's final drives were simpler, more robust designs with larger safety margins. They were deliberately over-engineered to handle abuse. And they were made from materials that American industry could produce consistently. The fuel consumption comparison was equally revealing. They ran both engines on dynamometers to measure consumption at various power settings. At cruise power, the Ford GAA consumed approximately 1.4 gallons per mile. The Maybach consumed 2.1 gallons per mile. The Sherman can operate 50% longer on the same fuel, Becker calculated. In 1945, with fuel shortages crippling our operations, this is decisive. The cooling systems told another story. The Sherman used a simple, robust radiator with large cooling passages and a powerful fan. The system was almost impossible to overheat under normal conditions. The Panther's cooling system was more sophisticated but also more fragile. Smaller passages that could be blocked by debris. Vulnerable radiator positioning. Multiple reports of cooling failures in combat. The American system is designed assuming it will be maintained by barely trained crews under field conditions, an engineer noted. The German system assumes expert maintenance in proper facilities. Reality favors the American approach. They test-ran both engines for 4 hours continuously at various power settings, monitoring temperatures, pressures, and performance. The Ford GAA ran smoothly throughout, maintaining consistent power output. Oil pressure remained stable. Temperatures stayed within normal ranges. The Maybach ran well initially but developed concerning symptoms after 2 hours. Oil pressure fluctuated. One cylinder showed reduced power output. Cooling system temperature crept toward the high end of acceptable range. This engine needs maintenance, the chief mechanic concluded. Nothing catastrophic yet, but multiple developing problems. If we continued running it hard, we'd have failures within another few hours. Hauptmann Becker summarized the reliability findings bluntly. The Panther engine produces more power, but it's unreliable under combat conditions. It requires constant expert maintenance. It consumes fuel we don't have. It breaks down regularly. The Sherman engine is less powerful but works consistently. Given the choice between 700 unreliable horsepower and 500 reliable horsepower, I'd take the reliable option every time. Muller wrote in his report, engine reliability comparison strongly favors the American design. The Ford GAA prioritizes consistent operation over maximum power output. Simpler design, robust construction, and wide safety margins make it suitable for operation by minimally trained crews under field conditions. The Maybach HL230 produces superior power but requires maintenance intensity and quality we can no longer provide. In practical terms, the Sherman's engine is superior for actual combat operations despite lower peak performance. It was another uncomfortable truth. German engineering sophistication had become a liability when manufacturing quality declined and maintenance capacity collapsed. The armor comparison seemed straightforward on paper. The Panther had 80 mm of sloped frontal armor at 55 degrees, providing effective thickness of approximately 140 mm. The EZ-8 Sherman had 64 mm of frontal armor at 47 degrees, giving effective thickness of around 90 mm. Clear advantage, Panther. But when the German evaluation team examined actual combat effectiveness of armor protection, the picture became more complex. Muller had obtained after-action reports from both German and American tank units. He spread the data across a table and asked the team to analyze it. Look at crew survival rates, Muller directed. When a Sherman is penetrated, what percentage of the crew survives? When a Panther is penetrated, what percentage survives? The data showed something unexpected. Sherman crews had significantly higher survival rates when their tanks were knocked out. Panther crews often died with their tanks. Why? Muller asked. Hauptmann Becker had the answer immediately. Ammunition fires. When a Panther is penetrated, the ammunition often ignites. The fire spreads rapidly through the fighting compartment. Crews have seconds to escape, if they can escape at all. He pointed to the EZ-8. But this Sherman variant has what the Americans call wet stowage. Let's examine it. They opened the Sherman's hull and looked at the ammunition storage. The 76mm rounds were stored in armored bins surrounded by water glycol jackets. If a penetrating round hit an ammunition rack, the liquid would absorb heat and suppress ignition. This is why they stopped calling it the Tommy Cooker, Schmidt observed. Earlier Shermans stored ammunition throughout the hull. Any penetration risked catastrophic fire. This wet stowage system dramatically reduces that risk. The German engineers tested the system by examining battle-damaged Shermans recovered from various battlefields. Tanks with wet stowage that had been penetrated showed far less fire damage than earlier models. Many had been penetrated multiple times but hadn't burned. The Americans learned from their losses and redesigned the ammunition storage, one engineer noted. We identified the problem years ago but never implemented a similar solution. We accepted the crew loss rate as unavoidable. The crew protection features throughout the EZ-8 revealed a design philosophy focused on keeping crews alive. The driver and assistant driver positions had additional armor plates protecting them from frontal hits. The turret had an armored basket that rotated with it, protecting the crew from hull spalling. Most significantly, the EZ-8 had multiple escape hatches. The commander had a large hatch. The loader had a hatch. The driver and assistant driver had hatches. If the tank was hit and burning, crews had multiple exit options. The Panther had fewer escape routes. The crew hatches were smaller. In combat conditions, with the turret potentially jammed or blocked, escape could be impossible. The Americans designed tanks assuming they will be hit, Becker said. They focus on keeping crews alive after penetration. We design tanks trying to prevent penetration, but when it happens, we provide minimal crew protection. The engineers examined the armor quality itself. Both tanks used rolled homogeneous armor, but there were differences in metallurgy and manufacturing. The Sherman's armor plates showed consistent quality. The steel was uniform throughout. Face hardening was even. No significant flaws or inclusions visible. The Panther's armor plates, particularly on late production vehicles like their test tank, showed quality problems. Inconsistent hardening. Metallurgical flaws. Some plates had visible cracks near weld seams. This is another late-war production issue, an engineer explained. We're using substitute alloys because we lack proper alloying elements. The armor is technically the right thickness, but the metallurgical quality has degraded. It's more brittle, more prone to cracking when hit. They conducted ballistic tests using captured weapons. At 500 meters, an American 76mm HVAP round penetrated the Panther's frontal armor at perpendicular impact. At angles, it sometimes penetrated, sometimes ricocheted, depending on the exact angle and impact point. The Sherman's thinner frontal armor was more easily penetrated by the Panther's 75mm gun, as expected. But the wet stowage system meant penetration didn't automatically result in catastrophic loss. In a frontal engagement, the Panther has the advantage, Vogel concluded. But in fluid combat with flank shots common, the Sherman's crew protection features are more valuable. Dead crews can't fight even if the tank is theoretically superior. The vision systems revealed another protection-related difference. The Sherman had excellent vision devices, periscopes, vision ports, and commander's cupola providing good situational awareness. Crews could see threats approaching. The Panther's vision systems were adequate but not exceptional. The commander's cupola provided decent visibility, but the driver's vision was limited. Panther crews often reported being surprised by threats they didn't see approaching. Situational awareness is protection, Schmidt noted. If you see the threat first, you can maneuver or fire first. The Sherman's crew has better awareness of their surroundings. The armor layout also differed philosophically. The Panther's armor was optimized for frontal protection, with weaker side and rear armor. This made sense if you assumed tanks would primarily fight hull down or in defensive positions. The Sherman's armor was more evenly distributed. Less frontal protection, but better all-around coverage. This made sense for tanks expected to fight in mobile, fluid situations where threats could come from any direction. The Panther is designed for defense, Becker observed. Position it properly, and it's very difficult to kill. But in mobile warfare, where flanks are constantly exposed, the more balanced Sherman armor is actually more survivable. The evaluation team examined crew injury reports from knocked-out tanks. The data showed Sherman crews suffering fewer severe injuries when their tanks were hit. The armor layout, spall liners, and crew positions all contributed to better survivability. Panther crews suffered more severe injuries from spalling, ammunition fires, and the difficulty of rapid egress from damaged tanks. Muller summarized the armor findings. The Panther has superior frontal armor thickness and, when properly positioned, is more difficult to destroy. However, the Sherman's balanced protection, crew safety features, and wet ammunition storage provide better overall crew survivability. In total war where trained crews are irreplaceable assets, preserving crews may be more important than preserving tanks. American design philosophy prioritizes the crew. German design prioritizes the machine. The American approach is proving more effective strategically. It was perhaps the most damning conclusion yet, that German tanks protected the vehicle better but the men worse, while American tanks did the opposite, and in practice, protecting the men mattered more. On the evaluation's fourth day, Muller had both tank crews switch positions repeatedly, experiencing every station in both the Sherman and the Panther. He wanted to understand how crew efficiency and coordination differed between the two designs. Hauptmann Becker started in the Sherman's commander position. The turret was cramped compared to the Panther, but everything was positioned logically. The commander's cupola provided excellent visibility with 6 periscopes offering near 360-degree vision. Most importantly, the Sherman had something the Panther lacked, a proper intercom system that actually worked. Test communications, Becker ordered over the intercom. Driver clear, came the immediate response. Gunner, clear. Loader, clear. Assistant driver, clear. Every crew position heard him clearly. No static. No distortion. Crystal clear communication throughout the tank. In the Panther, the intercom system was temperamental at best. It worked sometimes, failed often, and was regularly so full of static that crews gave up using it and reverted to shouting over the engine noise. Communications are critical in combat, Becker noted. The commander needs to direct the crew instantly. Delays or miscommunication get you killed. The Sherman's intercom is a significant tactical advantage. He examined the commander's station more closely. The controls for the turret traverse were at hand. The gun triggers were accessible for override. The radio was within easy reach. Everything a commander needed was positioned where he could access it without moving from his position. The vision cupola could rotate independently of the turret, allowing the commander to scan for threats while the gunner engaged a target. This division of labor made the crew more effective. In the Panther, the commander's position was similar in concept but less refined in execution. The cupola was good, but the controls were less ergonomically arranged. The radio was harder to access. Small inefficiencies that added up in combat. Lieutenant Vogel took the gunner position in both tanks. In the Sherman, he found the station well designed for sustained operation. The seat was adjustable. The gun sight was clear and well positioned. The gun controls were responsive and easy to use. The gyro stabilizer controls were intuitive. Flip a switch, and the gun would maintain rough elevation even as the tank moved. Flip it off for stationary precision firing. This station is designed for average gunners, Vogel observed. Everything is straightforward. A crew member with basic training can become effective quickly. There are no complex procedures or techniques requiring extensive experience. In the Panther, the gunner's position was more sophisticated but also more demanding. The gun sight was excellent, but operating it effectively required more training. The gun controls were precise but less forgiving of operator error. The Panther's gunnery system is designed for expert gunners, Vogel concluded. In the hands of an experienced crew, it's superior. But we're training replacement crews with weeks of instruction instead of months. The Sherman's simpler system produces better results with the crews we actually have. The loader positions revealed another significant difference. In the Sherman's turret, the ready ammunition racks were positioned perfectly for the loader to grab rounds quickly without moving his feet. The spent shell casing ejection system threw empties out automatically, keeping the fighting compartment clear. The loader could sustain 8 to 10 rounds per minute almost indefinitely without exhaustion. In the Panther, the loader had to work harder. The ammunition storage required more reaching and maneuvering. Spent casings had to be manually stowed or kicked aside. After 20 or 30 rounds, the loader would be exhausted and the rate of fire would decline. Sustained rate of fire matters in combat, Schmidt observed. The first few shots might be similar, but after 5 minutes of continuous engagement, the Sherman crew will still be operating effectively while the Panther crew is tiring. The driver positions showed the starkest contrast. In the Sherman, the driver sat in a reasonably comfortable seat with good forward visibility through a periscope. The controls were straightforward: steering levers, accelerator, brake. The transmission was a synchromesh design that allowed smooth gear changes. Any truck driver could learn to drive a Sherman competently in a few hours. In the Panther, the driver's position was more demanding. The steering system was heavy and required significant physical effort. The transmission was complex and unforgiving. Inexperienced drivers regularly ground gears or stalled the engine. "We designed the Panther for professional tank drivers," Becker said. The Americans designed the Sherman for soldiers who might have been farmers or shopkeepers 6 months earlier. Their approach produces a combat-effective crew faster. The turret basket was another revelation for the German team. In the Sherman, the crew stood on a basket that rotated with the turret. This meant the crew's orientation never changed relative to their stations. The loader always faced the ammunition racks. The gunner always faced the breech. Everything remained in position. In the Panther, the crew stood on the hull floor while the turret rotated above them. This meant the loader had to move around the rotating equipment, dodging the recoiling gun, maintaining balance while the turret turned. It was workable but less efficient. "The turret basket is simple but brilliant," an engineer noted. "It improves crew efficiency significantly. And it provides another benefit. It keeps the crew isolated from the hull, reducing injury from spalling if the lower hull is penetrated." The crew coordination during mock engagements demonstrated the cumulative effect of these design differences. They ran both tanks through simulated combat scenarios, engaging multiple targets in sequence while maneuvering. The Sherman crew, even though they were German tankers unfamiliar with the tank, achieved good performance. The commander could communicate clearly. The gunner could acquire and engage targets efficiently. The loader could sustain fire. The driver could maneuver without constant instruction. The Panther crew, operating their own tank with which they were thoroughly familiar, performed well but showed more strain. Communication was harder. Crew coordination required more effort. Physical exhaustion set in faster. "The Sherman is a cruise tank," Becker concluded. "It's designed to make the crew effective. The Panther is a tank that requires an effective crew. Both work, but the American approach is more forgiving of average personnel and combat stress." Muller documented the crew efficiency findings carefully. The Sherman M4A3E8 incorporates numerous features that enhance crew performance: excellent intercom system, ergonomic control layout, turret basket, accessible ammunition storage, clear vision devices, and intuitive operation. These features multiply the effectiveness of average crews. The Panther has superior individual characteristics but places higher demands on crew skill and endurance. In sustained operations with tired crews, the Sherman's crew-friendly design provides a cumulative advantage. He added a final observation: "We designed our tanks for peacetime-trained professional soldiers. The Americans designed their tanks for wartime-trained citizen soldiers. Their design philosophy matches the reality of total war better than ours." The comprehensive mobility trials began on the 5th day with both tanks fully fueled and ready for extended testing. Muller had designed a series of challenges that would push both tanks to their operational limits. The first test was simple acceleration. Both tanks lined up on a measured kilometer straight section. On signal, both would accelerate to maximum speed. The Panther launched aggressively, its 700 horsepower engine roaring. The tracks bit into the ground, and the 45-ton tank surged forward. It hit 30 km per hour quickly, then continued accelerating to 40, 45, finally reaching 52 km per hour before the measured kilometer ended. The EZ-8's acceleration was different. Smoother. Less dramatic initially. But by the halfway point, it was matching the Panther's speed. At the finish, it recorded 48 km per hour. 4 km per hour slower, Schmidt noted. As expected, with less power. But then Muller changed the test. Now repeat the acceleration, but on that rutted section of the course. This was where everything changed. The Panther accelerated aggressively but had to slow significantly when it hit the rough surface. The violent pitching made it impossible to maintain speed. It completed the rough kilometer at 32 km per hour average. The EZ-8 accelerated into the same section. The HVSS suspension absorbed the rough terrain smoothly. The tank maintained 41 km per hour average through the section, nearly 30% faster than the Panther. On roads, the Panther is faster, Becker observed. On rough terrain, the Sherman is faster. And we're not fighting on roads anymore. The hill climbing tests were next. A steep 30-degree slope with loose soil at the crest. Both tanks attacked the hill from a standing start. The Panther charged up the slope, tracks churning. But near the crest, where the soil was loosest, the narrow tracks began losing traction. The tank slowed, churned, and barely made it over the top after several attempts. The EZ-8 approached the same hill. The wider tracks, with their lower ground pressure, bit into the loose soil more effectively. The tank climbed steadily and crested the hill on the first attempt without drama. Ground pressure, an engineer calculated quickly. The Panther has 13.8 pounds per square inch. The EZ-8 has 10.5 pounds per square inch. That 24% difference is decisive on soft ground. They tested this principle further by driving both tanks across a muddy field. The Panther sank deeper, leaving deeper ruts, and required more power to maintain forward motion. In several spots, it nearly bogged down. The EZ-8 crossed the same field more easily. The wider tracks distributed weight better. It floated over terrain where the Panther struggled. The turning tests revealed another advantage. They marked a circle and measured how tightly each tank could turn at various speeds. The Panther's turning radius was larger, especially at speed. The long wheelbase and complex steering system made tight turns difficult. At slow speeds, it could pivot turn effectively, but this consumed tremendous fuel and put stress on the drivetrain. The EZ-8 turned more tightly at all speeds. The shorter wheelbase and simpler steering made it more maneuverable in confined spaces. In urban terrain or forest roads, this would be a significant tactical advantage. The Sherman can maneuver where the Panther can't, Schmidt said, after driving both tanks through a course marked with obstacles simulating buildings and rubble. In close terrain, maneuverability matters more than maximum speed. The endurance test was the most revealing. Both tanks received full fuel loads and were driven on a measured circuit that included roads, cross-country sections, and obstacles. They would run until fuel exhaustion. The Panther, burning over 2 gallons per mile, exhausted its fuel after approximately 90 kilometers. It ran strong initially, but the heavy fuel consumption meant limited range. The EZ-8, burning 1.4 gallons per mile and carrying more total fuel, covered 150 kilometers before running dry. Nearly 70% more range from a single tank of fuel. Operational radius matters, Becker noted grimly. In 1945, with fuel shortages crippling our operations, the Sherman's efficiency is a massive advantage. We often can't fuel Panthers for long-range operations even when we have Panthers available. They conducted speed tests on various surfaces. On paved roads, the Panther maintained its speed advantage, 52 km per hour versus 48 km per hour. But paved roads were increasingly rare in war-torn Europe. On dirt roads, the speeds equalized, 42 km per hour for both tanks. On rough terrain, the Sherman pulled ahead, 35 kilometers per hour versus 28 kilometers per hour. Through forests and obstacles, the gap widened further in the Sherman's favor. The Panther is faster on paper, Muller noted. But actual tactical mobility across realistic terrain favors the Sherman. The superior suspension and lower ground pressure allow it to maintain higher speeds where it matters. The obstacle crossing tests showed the EZ8's HVSS suspension at its best. Log obstacles, ditches, rubble fields, the Sherman navigated everything smoothly while maintaining speed. The crew inside was joshed but not hammered. The Panther crossed the same obstacles but required slower speeds and more careful navigation. The crew was thrown around more violently. After an hour of obstacle navigation, the Panther crew was exhausted. The Sherman crew was still fresh. Crew fatigue is real, Becker said. After 6 hours of combat maneuvering in a Panther, crews are physically exhausted just from being thrown around inside the tank. The Sherman crew can fight longer because the tank beats them up less. The final mobility test was the most telling. Both tanks ran a 50-kilometer mixed course including all terrain types, then immediately engaged targets at the end. This simulated a road march followed by immediate combat. The Panther completed the course but arrived with the crew tired and the tank showing stress. Oil pressure was elevated. Engine temperature was high. The final drives were hot. The crew needed rest before engaging effectively. The EZ8 completed the course with the crew relatively fresh and the tank running coolly. They engaged targets immediately and performed well. This is the reality of armored warfare, Becker concluded. Tanks don't just fight battles. They maneuver to battles, sometimes for hours or days. The tank that arrives ready to fight has the advantage. The Panther pushes its crew and its systems hard just getting to the fight. The Sherman arrives ready to engage. Muller's mobility assessment summary was unequivocal. Despite lower power output, the M4A3E8 demonstrates superior practical mobility across realistic terrain. The HVSS suspension, wider tracks, lower ground pressure, better fuel efficiency, and crew-friendly characteristics combine to produce a tank that can maneuver faster, farther, and with less crew fatigue than the Panther. On paved roads, the Panther is faster. In actual combat conditions across mixed terrain, the Sherman is more mobile. The German team had entered the evaluation believing the Panther's 700 horsepower made it the more mobile tank. They were learning that mobility was about far more than just power. Heinrich Muller saved what he considered the most strategically important analysis for the final day: manufacturing efficiency and field maintenance capability. Gentlemen, he told his team, a tank that takes 6 months to build and breaks down every 100 kilometers is less valuable than a tank that takes 6 weeks to build and runs for 1,000 kilometers. Let's understand which tank is which. The engineers began by completely disassembling major components from both tanks, documenting every part and analyzing how it was manufactured. The EZ8's construction immediately revealed a design philosophy oriented toward mass production. The hull was made from large, flat armor plates welded together at simple angles. The welds were heavy and obvious, not the refined work of master craftsmen, but they were strong and consistent. These welds were done by semi-skilled workers, possibly women, one engineer observed. You can see the technique is straightforward. Not beautiful, but effective. They've designed the hull so that average welders can produce acceptable results. The Panther's hull was more complex. The interlocking armor plates required precise fitting. The welds had to be exact because improper welding could compromise the carefully calculated armor angles. It required skilled welders working carefully. The Panther hull takes approximately 55,000 man-hours to complete from raw materials to finished tank, Muller stated, consulting production data. The Sherman takes approximately 10,000 man-hours. The Americans build a Sherman in the time we need to build 1/5 of a Panther. The component analysis was equally revealing. The engineers laid out comparable parts from both tanks: road wheels, track links, gun components, transmission parts. The Sherman parts showed consistent manufacturing quality. Every road wheel was identical. Track links were interchangeable. Tolerances were held throughout production. These were parts made by automated or semi-automated processes with good quality control. The Panther parts showed more variation. Some components were excellent, others showed manufacturing shortcuts. Tolerances varied. The quality depended on when and where the part was made as German manufacturing standards collapsed under Allied bombing. Interchangeability matters enormously for field maintenance, Becker noted. If a Sherman road wheel breaks, any replacement will fit. If a Panther component fails, we often need to fit and adjust the replacement because parts aren't truly interchangeable. They conducted simulated field repairs to test maintenance accessibility. First challenge: replace a damaged road wheel on both tanks. For the EZ-8, 2 mechanics removed the damaged wheel in 25 minutes using basic tools. The HVSS suspension made access easy. Bolt off the old wheel, bolt on the new one. No adjustment needed. For the Panther, the same repair took over 2 hours. The interleaved road wheels meant they had to remove 3 wheels to access the damaged one. Then reinstall all of them. The complex suspension required careful adjustment. In combat, speed of repair matters, Schmidt observed. A Sherman disabled by track damage can be back in action in an hour. A Panther might be down for half a day. The engine accessibility test was even more dramatic. They simulated combat damage requiring engine replacement. The Sherman's engine compartment was designed for rapid access. Large hatches opened easily. The engine mounts were simple. Disconnect a dozen connections, unbolt the mounts, lift out the engine. Install the new engine in reverse order. A 3-man crew with a hoist completed the swap in 3 hours. The Panther engine replacement they had tested earlier required nearly 7 hours, and that was in a proper maintenance facility with experienced mechanics and all necessary tools. In the field, under combat conditions, with tired crews and limited tools, that time difference becomes even more pronounced, Muller noted. The Sherman can be repaired at the front. The Panther often needs to be recovered to rear area facilities. The track replacement test showed similar patterns. Sherman tracks used rubber and steel pads bolted to metal links. Replacing damaged sections was straightforward. The tracks were designed to be maintained by ordinary soldiers with basic training. Panther tracks were all-metal construction requiring more specialized tools and techniques. Track maintenance required more expertise and time. They examined the technical manuals for both tanks. The Sherman manual was comprehensive, clearly written, with detailed illustrations. It assumed the user had basic mechanical knowledge but not specialized tank expertise. Step-by-step procedures covered every common repair. The Panther manual assumed the reader was an experienced tank mechanic. It provided less detailed guidance, expecting the mechanic to understand complex procedures without extensive explanation. The American manual is written for the army they have, an engineer observed. Drafted civilians given basic training. The German manual is written for the army we wish we had, professional career soldiers with years of mechanical experience. The spare parts situation revealed the strategic implications most clearly. The EZ-8 used many standardized components shared across multiple vehicle types. The engine was used in other tanks and vehicles. The transmission was a modified truck unit. The electrical components were standard military issue. This meant spare parts were available throughout the supply chain. A Sherman needing repairs could often cannibalize parts from damaged trucks or other vehicles. The Panther used specialized components unique to the tank. If you needed a Panther transmission, it had to come from Panther-specific supply chains. No alternative sources existed. Logistics determine what's possible in war, Becker said grimly. We've lost battles not because Panthers broke down, though they did, but because we couldn't get replacement parts to repair them. Broken Panthers become permanent losses because we lack the parts and facilities to fix them. The manufacturing quality comparison was perhaps most painful for the German engineers. They examined components from the EZ-8 with magnifying glasses and measuring instruments. This is consistent, high-quality manufacturing at industrial scale, the chief engineer concluded. These components show no variation in quality. Every part meets specifications. This is only possible with sophisticated quality control and industrial processes we can no longer maintain. He compared them to late-war Panther components. Our components vary significantly in quality. This transmission gear shows improper heat treatment. This armor plate has metallurgical flaws. This bearing is made from substitute alloys because we lack proper bearing steel. We're trying to maintain 1942 standards with 1945 resources and failing. The maintenance interval comparison was sobering. The Sherman required basic service every 500 kilometers, oil change, filter inspection, track adjustment. Major service every 3,000 kilometers. The engine was rated for 10,000 kilometers between overhauls. The Panther required service every 150 kilometers. Major service every 800 kilometers. The engine needed overhaul or replacement after 1,500 to 2,000 kilometers, and that was under optimal conditions. The maintenance burden of Panthers is crushing our logistics, Becker admitted. We spend more time maintaining Panthers than fighting with them. The Sherman requires 1/3 the maintenance effort for 3 times the operational time. Muller's manufacturing assessment concluded, the M4A3E8 represents mature industrial design optimized for mass production and field sustainability. It requires 1/5 the manufacturing time, uses interchangeable components, can be maintained with basic tools by minimally trained crews, and operates reliably for extended periods between service. The Panther represents sophisticated engineering that our industrial base can no longer support. We cannot manufacture it in sufficient quantities with acceptable quality, cannot supply adequate spare parts, and cannot maintain it effectively in field conditions. The Sherman is the superior tank not because of any single performance metric, but because it can be produced, deployed, and sustained in numbers that matter strategically. It was the most comprehensive condemnation yet. The Panther was an excellent tank Germany couldn't afford to build, while the Sherman was a good tank America could build by the thousands. On the evening of the 6th day, Heinrich Müller gathered his evaluation team in the conference room. Before them lay 6 days of data, measurements, observations, and field testing. Now came the difficult task, writing the official assessment that would go to high command. The tension in the room was palpable. Everyone understood that their conclusions would not be welcomed by leadership that had invested enormous resources in Panther production and had told German soldiers that their tanks were superior. Müller began with a direct question. Based on everything we've observed, which tank would you rather take into combat? Assume adequate fuel, ammunition, and a crew with 3 months of training. The Panther or the Easy 8 Sherman? The 3 combat veteran tank commanders exchanged glances. Finally, Hauptmann Becker spoke. 6 months ago, I would have said the Panther without hesitation. After this evaluation, I would take the Sherman. Schmidt nodded agreement. The Panther is theoretically superior in armor and firepower. But the Sherman works. It starts reliably. It drives wherever I need to go. It can fight all day without breaking. I can repair it with basic tools. Those practical advantages outweigh the Panther's theoretical superiority. Lieutenant Vogel added, from a gunnery perspective, the gyro stabilizer gives the Sherman a first-shot advantage in mobile combat. The Panther has the better gun for long-range static defense, but we're not fighting that kind of war anymore. We're fighting on the move, in close terrain, with flanks constantly exposed. The Sherman is designed for the war we're actually fighting. Müller made notes, then posed another question. What would you tell a Panther crew facing Easy 8 Shermans in combat? Becker answered immediately. Don't engage at close range if you can avoid it. Use your superior long-range gun. Don't let them get to your flanks. Don't assume your frontal armor will protect you. Their HVAP rounds can penetrate under the right conditions. And most importantly, don't expect to outmaneuver them. They're faster cross-country and more agile in close terrain. In other words, Müller said, the tactical advice is essentially defensive. Avoid the Sherman's strengths rather than exploiting the Panther's advantages. Yes, Becker admitted. Because in a fluid engagement at typical combat ranges, the Sherman has more advantages than the Panther. The engineers provided their assessment of the technical comparison. The Sherman represents a fully mature design that has evolved through years of combat feedback. Every system has been refined and optimized. The result is a tank with no revolutionary features but excellent integration of proven technologies. He continued, the Panther is a more ambitious design with better individual specifications, but it's also less reliable, harder to maintain, and increasingly difficult to manufacture with acceptable quality. In the context of March 1945, with our industrial capacity collapsing, the Sherman's design philosophy is superior. Muller spent 2 days writing the comprehensive evaluation report. The document was detailed, technical, and unsparing in its conclusions. The executive summary would determine whether anyone read the full report, so Muller crafted it carefully. The American M4A3E8 Sherman, when compared directly to the German Panther OSG, demonstrates the following characteristics. Superior practical mobility across all terrain types despite lower power output. The HVSS suspension and lower ground pressure provide better cross-country performance. Comparable combat effectiveness with advantages in mobile warfare. The gyro stabilizer and superior crew coordination enable effective fire on the move. The 76mm gun with HVAP ammunition can defeat Panther armor at typical combat ranges. Vastly superior reliability and maintainability. The Sherman requires 1/3 the maintenance effort and operates 3 times longer between major services. Better crew survivability due to wet ammunition storage, multiple escape hatches, and crew-friendly design features. More efficient logistics. Better fuel economy, interchangeable parts, and simpler maintenance reduce the logistical burden by approximately 60%. Faster production time by a factor of 5, using simpler manufacturing processes suitable for semi-skilled labor. Overall assessment. In the context of total war requiring sustained operations with limited resources, the M4A3E8 Sherman is the more effective combat tank than the Panther. The Panther's advantages in armor protection and gun penetration are offset by the Sherman's advantages in reliability, maintainability, crew efficiency, and logistical sustainability. The report included a section on strategic implications that Muller knew would be controversial. Germany's focus on producing technically superior tanks in limited numbers has proven strategically inadequate. The Americans produce 5 Shermans for every Panther we manufacture. Even if each Panther could defeat 3 Shermans in combat, which combat reports indicate is not consistently achievable, the numerical imbalance renders German qualitative superiority irrelevant. Furthermore, the Panther's maintenance requirements and fuel consumption exceed our current logistical capacity. We are fielding tanks we cannot adequately support. Many Panthers are lost to mechanical failure or abandonment due to fuel shortages rather than enemy action. The Sherman's design philosophy, adequate performance, high reliability, sustainable logistics, is more appropriate for protracted warfare than our pursuit of maximum technical performance. This evaluation suggests fundamental reconsideration of German armored vehicle development priorities. Muller concluded with recommendations that he knew were already too late to implement. Immediate recommendations: modify Panther production to improve reliability even at the cost of some performance. Simplify manufacturing processes. Improve parts interchangeability. Long-term recommendations: future German tank designs should prioritize reliability, maintainability, and production efficiency over maximum performance specifications. The American approach of building good tanks in large numbers defeats our approach of building excellent tanks in small numbers. The report was completed on March 17, 1945. Muller signed it, his engineers signed it, and the 3 tank commanders added their endorsements. The document was classified secret and sent through channels to the Waffenamt headquarters in Berlin. It arrived during a period of chaos. Berlin was under increasingly heavy bombing. The Eastern Front was collapsing. The Western Allies had crossed the Rhine. The German High Command had more pressing concerns than a technical evaluation of enemy tanks. The report was filed and largely forgotten. Some copies reached field commanders who found the findings consistent with their combat experience but were powerless to change production priorities. A few engineers read it with grim recognition that their warnings about reliability and production efficiency had been validated, but too late to matter. The captured EZ-8 remained at Kummersdorf for another month before the facility was evacuated ahead of Soviet advances. The tank was destroyed to prevent recapture, along with most of the other test vehicles and equipment. The evaluation team dispersed. Becker returned to his unit and was killed in action near Berlin in April. Schmidt survived the war and spent 3 years in Soviet captivity. Vogel was captured by American forces and released in 1946. Muller disappeared in the chaos of Berlin's fall, and his fate was never confirmed. The report itself surfaced after the war when American investigators examined captured German documents. It was translated and studied by U.S. Army analysts who found its conclusions aligned with American combat assessments. One American tank officer who read the translated report noted in the margin, "The Germans figured out what we'd been saying all along. The Sherman isn't the best tank. It's the best tank we could build in the numbers we needed, and that made it better than anything else." The evaluation had confirmed what practical experience already showed, that in modern warfare, the tank that can be produced, deployed, maintained, and sustained in adequate numbers will defeat the theoretically superior tank that exists in insufficient quantities. Germany had learned this lesson through bitter experience. But by March 1945, learning the lesson changed nothing. The war was already lost. The story of the captured EZ-8 evaluation ended in March 1945, but its lessons echoed long after the war concluded. When American forces overran Kummersdorf in May 1945, they found the destroyed remains of their Sherman among the wreckage of German test vehicles. The tank that had revealed so much to German engineers was now just twisted metal and burned components, deliberately destroyed to prevent its recapture. But the knowledge gained from that evaluation lived on in documents, in the memories of survivors, and ultimately in the post-war understanding of what had made Allied victory possible. The EZ-8 Sherman went on to prove everything the German evaluation had documented. In the final months of the war in Europe, EZ-8s equipped American armored divisions pushing into Germany. They performed exactly as the evaluation predicted: reliable, mobile, effective. They couldn't always defeat Panthers or Tigers in frontal armor duels, but they didn't need to. They maneuvered around German strongpoints. They exploited their superior mobility and reliability. They arrived at battles ready to fight while German tanks broke down en route. They kept fighting after German tanks ran out of fuel. The numbers tell the story. By war's end, America had produced approximately 49,000 Sherman tanks in all variants. Germany produced approximately 6,000 Panthers. The EZ-8 alone numbered over 4,000 units produced between 1944 and 1945. When the shooting stopped in May 1945, hundreds of operational EZ-8s remained in service. Most Panthers still running had been captured by advancing Allied forces. The majority had been abandoned due to mechanical failure or fuel exhaustion rather than combat damage. The EZ-8 continued serving long after World War II ended. When war erupted in Korea in 1950, EZ-8s formed the backbone of American armored forces. They proved effective against Soviet-supplied T-34 tanks, demonstrating that their combination of firepower, mobility, and reliability remained relevant even 5 years after the war's end. Some EZ-8s served into the 1950s with Allied nations. Israel used Shermans, including EZ-8s, through multiple conflicts. Other nations operated them into the 1970s. The design's fundamental soundness meant that with upgrades and modifications, the basic platform remained militarily useful decades after its introduction. The German evaluation team's insights about tank design philosophy influenced post-war thinking in surprising ways. When the United States began developing new tanks in the 1950s, the lessons of reliability and maintainability remained central to design requirements. The M48 Patton, America's first major post-war tank design, incorporated EZ-8 lessons, emphasis on crew comfort and efficiency, robust construction, maintainable systems, and design for sustained operations. The philosophy of good enough in large numbers, evolved into excellent in adequate numbers. Meanwhile, post-war Germany, when it began rebuilding armored forces in the 1950s, took a different lesson from their wartime experience. The Leopard 1 tank, Germany's first post-war design, emphasized mobility and firepower over heavy armor, learning that survivability came from not being hit rather than absorbing hits. Interestingly, the Leopard 1 also incorporated reliability and maintainability as primary design requirements. German engineers had learned from the Panther's failures. The new tank had to work, not just perform impressively on paper. Survivors of the evaluation team rarely spoke publicly about their work. In post-war Germany, admitting that you had concluded American tanks were superior was not a popular position. But in private conversations and technical papers, some of the engineers involved shared their insights. One engineer wrote in a 1960s technical journal, "We learned too late that war is not won by the best tank, but by adequate tanks in sufficient numbers, properly supported. The Americans understood this from the beginning. We understood it only when the war was already lost." The EZ-8 evaluation represented a moment of clarity for German military technical staff. For 6 days in March 1945, ideology and propaganda were set aside, and professionals examined reality objectively. Their conclusions were uncomfortable but accurate. The Sherman wasn't invincible. It wasn't the best armored tank. It didn't have the most powerful gun. But it was reliable, maintainable, producible, and effective. It could be operated by average crews, maintained with basic tools, and sustained by practical logistics. These unglamorous virtues proved more valuable than any amount of technical sophistication. The German obsession with technical excellence, with building the best tank regardless of cost or complexity, had produced impressive machines that couldn't be produced in adequate numbers, maintained in field conditions, or supported logistically. The Panthers, Tigers, and other technically ambitious designs were masterpieces of engineering that arrived too late, in too few numbers, with too many mechanical problems. The EZ-8 Sherman represented the opposite philosophy. Build a good tank that works, that crews can rely on, that can be produced by the thousands, and that will still be running when technically superior enemy tanks have broken down or run out of fuel. In total war, that philosophy proved decisive. Today, only a handful of EZ-8 Shermans survive in running condition. They appear at military vehicle shows and museums, still operational 75 years after their manufacture. Their continued functionality is itself a testament to the design philosophy behind them. Build it simple, build it robust, build it to last. The comparison between the EZ-8 and the Panther remains instructive for modern military planners. The tension between technical excellence and practical effectiveness still exists. Should you build the most capable system possible, or the most sustainable system that's adequate for the mission? History suggests the answer. In protracted conflict, sustainability and reliability defeat sophistication and complexity. The German evaluation team understood this by March 1945. But understanding came too late to change anything. The industrial and logistical decisions that determined the war's outcome had been made years earlier. The EZ-8 Sherman proved that sometimes the best solution is the one that works reliably, can be produced in adequate numbers, and will still be operating when the theoretically superior alternative has failed. It wasn't the perfect tank. It was the right tank. And in war, that distinction matters more than all the armor thickness and gun penetration statistics combined. The fork-tailed devil of the previous evaluation had taught Germans about American air power. The EZ-8 taught them about American industrial philosophy applied to ground warfare. Both lessons came too late to affect the war's outcome. But they helped explain why Germany lost, not because German soldiers lacked courage or skill, but because Germany fought an industrial war with craftsman-era thinking. The EZ-8 Sherman stands as a monument to practical engineering defeating perfectionist ambition, to reliability triumphing over sophistication, to the idea that good enough in overwhelming numbers beats excellent in insufficient quantities. Those German tankers who examined the EZ-8 in March 1945 understood this truth completely. They just understood it too late to matter for their nation's survival. The war ended 6 weeks after the evaluation was completed. The The captured EZ-8 was destroyed. The reports were filed and forgotten. But the lessons remained, encoded in post-war doctrine and tank design philosophy. Sometimes victory doesn't go to the best weapon. It goes to the best weapon that can actually be fielded in the numbers that matter, when it matters, where it matters. The EZ-8 Sherman was that weapon. And history proved it.